When you think about medical devices, you probably picture the hardware. But inside there's software, the unsung hero, running everything from massive hospital machines to the little health apps on your phone. And when that code goes wrong, well, for this kind of software, being reliable isn't just a nice feature, it's literally a matter of life and death. I mean, the stakes here are just incredibly high. A simple software error, the kind of glitch that might just be annoying in a video game, can have absolutely life-altering consequences in a hospital. And that's why the industry has a whole international standard dedicated to getting this exactly right. Let me put it this way. You wouldn't use the same exact blueprint to build a little garden shed as you would to build a skyscraper, right? The core idea is that the amount of planning, the rigor, the safety checks you do, it all has to match how bad things could get if something goes wrong. And that right there, that's the fundamental principle behind all of this. So here's the deal. Software failures in medical devices are not just digital problems. They have real physical consequences for real people. An incorrect calculation, a frozen screen, that can directly translate into patient harm. So to get a handle on these pretty unique risks, the industry leans on a very formal, structured process. It's called IEC 62304. And listen, this isn't just about doing some testing at the end. No, it's a framework for the entire life cycle of the software, from the very first idea all the way to its final update. And it's all built around one thing: patient safety. So here's the absolute genius of the IEC 62304 standard. It gets that not all medical software is created equal. I mean, an app that just shows you the hospital cafeteria menu is worlds apart from the software that controls an insulin pump. It just makes sense that the process you use to build them shouldn't be identical. The standard lays out a really clear three-step approach. First up, your team has to analyze the absolute worst-case scenario. What's the potential harm if the software fails? Then, based on that, you assign one of three safety classes. And finally, that class, A, B, or C, tells you exactly what development processes, what documentation, and what testing you have to do. All right, so what exactly are these classes? Let's break down the official definitions for Class A, B, and C, because once you get these, the whole framework just clicks into place. Let's start with the easy one, Class A. This is your lowest risk category. Think of it this way. Even if this software completely crashes and burns, it's just not possible for it to hurt a patient. Basically, from a health and safety point of view, the consequences are, well, nothing. Okay, moving up the ladder, we've got Class B. This is the middle ground. Here, a software failure could lead to a hazardous situation, and the result? Something defined as a non-serious injury. We're talking about something that's temporary or pretty minor, definitely not life-threatening. And then there's Class C. This is the big one. This is the highest, most critical category. This classification is only for software where a failure could actually lead to death or a really serious life-threatening injury. You can bet the stakes are at their absolute highest here. Okay, A, B, C. Got it. But what does that actually mean for the people writing the code? For the project manager trying to build a schedule? How do these letters actually change what a software team does day in and day out? Let's get into the practical side of things. This is where the rubber meets the road. We're going to translate that classification letter into a real, concrete set of tasks and documents. It's where the theory of risk slams right into the reality of software development. The rule of thumb is super simple. As you climb the ladder from Class A to B and then all the way to C, the required paperwork gets deeper, the design process gets way more formal, and the testing becomes a lot more intense. Just look at this table. It spells it out perfectly. Now, a basic software requirements doc, yeah, that's needed for everyone. But things get much more serious for Classes B and C. For them, you suddenly need a formal software architecture document and detailed design documents. And get this, for Class C, you even have to prove that the most critical parts of your code are walled off from everything else to control risk. That's a huge jump in how much work you have to do. And it's not just documentation. The testing gets way more intense too. Sure, some baseline stuff like system testing and keeping a bug list, that's for everybody. But the really deep, nitty-gritty verification, that's reserved for Classes B and C. We're talking about formally testing every little piece of code and meticulously checking how they all fit together. And that level of rigor makes perfect sense when you remember the higher potential for harm. You know what? To really nail this down, let's look at 3 quick real-world style examples of how this all plays out. Okay, on one side, you've got Class A. We're calling it the informer.
A perfect example is that hospital cafeteria menu app. If it breaks, what's the worst that can happen? You think they have lasagna, but they don't. No health risk. Now, compare that to Class B, the advisor. This could be an app that analyzes heart rate data to flag a potential problem for a doctor. If it fails to raise that flag, it could delay a diagnosis, and that could lead to a non-serious injury. The risk is there, it's real, but it's not immediately catastrophic.
All right, and now for the one that really keeps developers up at night, Class C.
We call this one the lifeline for a reason. The software that runs an insulin pump is a classic Class C example. A failure here, a simple math error, a glitch in the delivery command, could directly cause a fatal overdose or a life-threatening underdose. In this case, the software is the treatment, and its failure could be deadly. It demands the absolute highest level of engineering you can imagine.
Okay, let's zoom out for a second and tie this all together. Why does this whole system of A, B, and C matter so much? Well, it's all about building software with confidence. Confidence for the developer, the regulators, and, most importantly, for the patient. What makes this whole system so smart is that it's just logical. It's a rational framework that forces engineering teams to pour their most intense efforts into the software that carries the most risk. It makes sure that the code that could literally be the difference between life and death gets every last ounce of scrutiny it deserves. So I'll leave you with this question. Imagine you're the one using a medical device, and you discover a bug. Which safety class would you want to know its software was built under? The answer is pretty obvious, right? And that's exactly why this standard isn't just bureaucratic red tape. It's a lifesaver.